In this question, we're going to talk about inheritance, composition, and more. We're going to talk about what is the difference between inheritance and composition and what other options exist and how do we choose which of these options is the one that we need for our code. Why don't we take a look? Our first premise is we want to share code. And the reason we want to share code is to eliminate update anomalies. There are many places in our code where we're doing largely the same behavior. And it's the case that we want to make sure that if that behavior changes, it changes in all of those call sites, all of those places at the same time. It's not the case that they just happen to look the same today, but that they are fundamentally identical. And so a change in one place cascades to all places. One of the ways in which we might do that, if we saw that this duplication was in the form of methods that were similar between different objects, is to make use of inheritance, composition, or other approaches. Our second premise is that inheritance, composition, and some other approaches are one of the ways in which we might share code across types. The canonical example for something that we might call inheritance is we have some base type and it has some function f, and b and c both have the ability to make use of this function f without us to do any extra work at the b level or the c level just by inheriting from A. And so we can see all three of these types all have the ability to share this underlying method, this f method. Now, there's another approach that we can take. Instead of inheriting, we can compose. We can say that B is composed of an instance of the object of type A. So B has an instance of type A, and C has an instance of type A, and we can still make use of this shared logic. We can still make use of this function, but in this case, we have to route it through A. Here, A, B, and C all have access to this function f, but in the case of A, B, and C, we have to route it through this composed object, through this attribute. However, that's not necessarily the case because we could easily do a little bit of wrapping. We could say f equals a.f, or we could do something like write a full function here that returns self.a.f. So we can eliminate this one extra step and make it appear that A, B, and C all share this functionality, even though it is only written in its unique fashion in one place, where for all of the other use cases, they are written in such a fashion as to allow them to share without having to add any complexity themselves. Now, this approach does suggest to us that there is more than just inheritance and composition. In fact, there is one more approach that we have, namely the object construction approach. Nothing stops us from writing one instance of this function and then sharing it among these three classes, making use of this little quirk of the Python parser that we can assign a global variable into the body of the class like this. And so you can see A, B, and C all share this code for this function f, and it's only written in one place here. And this is largely what we call object construction because you can think that we could come up with our own mechanisms by which to add these methods. We could say f and g are two methods we want to share, and we could say something like methods is a set of f and g. And then in C, we could say, you know what I'm going to do? I'm going to do a locals dot update, and here I might update f and g. Maybe we'll make this a dictionary so we get both the name of this and the value of this. I want to update with methods. And so A, B, and C both share, or all share f, and C also has g. And you can think that this is kind of coming up with its own protocol for sharing things. Our next premise is that inheritance, composition, and object construction are materially different. There is a meaningful distinction between these, and we can judge which of these is appropriate for our use case by considering a couple of different things. One consideration is how transparent are these approaches? Oftentimes when we talk about inheritance and the transparency of inheritance, we're alluding to Liskov substitution. The idea that we can create a subclass and we can use it in the same places as the base class, that anywhere where the subclass can be used, the base class could also be used, or vice versa. And there's a little bit of theory there, but largely we can see how this applies. We might have type A, we might inherit from type A to create B. There might be some code that is reliant on looking at the object to make sure that it's of type A, and it's helpful that instances of type A and type B both are considered to be of type A. So this code path will be taken in both cases, even though here we might add some additional functionality, we might wrap some functionality, we might say here this does the original superclasses f plus some small modification to it. And all code that assumes that it's looking at just type A can actually also operate on this thing of type B. This is maybe why we want to use isInstance rather than a more strict check like if type of this object is A. Because here you can think that this is being a little bit too strict for our purposes. This is saying you must be exactly of this type and I'm not going to allow subtyping. And usually it's not the case that we want that. Now, in order to get these isInstance checks to work the way we want, we actually have some other options. Here you can see A and B are of different types. And I'm using the composition, and we cannot get the isInstance check to work appropriately in this case of the composition. We can see that the A attribute of B is of type A, but we're still limited in a way that we weren't limited in the inheritance case. However, almost all of the top-level syntax or the built-in functions have some hook point to allow you to customize them, and the hook point for isInstance is instance check as implemented on the meta class. And so here you can see a class with the meta class that implements instance check. This meta class says anything is considered to be an instance of this class kind. You can see A and B are not inheriting from kind whatsoever, but they are both indicated via this isInstance logic to be of type kind. What we can think here is the strict relationship between is this a kind of this thing, is this a type of this thing via that isInstance check and the class hierarchy. Well, we can actually customize that to our heart's content, and we can do things very similar to what collections.abc does. We can say this object is of this type as according to some arbitrary predicate, even though it's not necessarily inherited. And so in the case of this composition, we could use a mechanism very similar. We could say rather than check if you're exactly of type A, maybe you check if you're of some type T, and this type T uses the meta class isInstance or isInstance check to register both A and B. Here we can say type of the instance, let me do something like this, or is instance of this thing an A or a B. And here we can get around the limitation. So that's not really a requirement that we have to be strictly subclass from something in order to register ourselves as being of that type. We can always use some ad hoc protocol that we implement in order to make that work. Now, another consideration would be how affirmative are these approaches? Are these pull approaches or push approaches? And whose responsibility is the maintenance of this code sharing if one of the sides changes? Here's what I mean. If we use inheritance, you can see that type B has access to this shared code, has access to function f. And if class A changes later and adds in a function called g, type B automatically gets this. You can see that these are being pushed onto this type B without you having to affirmatively do anything. You don't have to explicitly say, oh, I want access to f and g. You just have to say, I want access to whatever A has, and you pass that through. And in the case of B, what you get to do is you get to say where you want to override, where you want to add some intermediation between the functionality that you automatically get and what you expose to the outside world. And so you can often see this is done via writing the shadowed method and then calling super. And here you can think that might be an implementation of something that we might do. In the case of composition, however, this is more of a pull technique. We have to affirmatively say, you know what, we want access to G when G is created by either explicitly wrapping it or explicitly passing it through. So you can think that if we don't want to be automatically responsive to changes in A, we want to be really picky about what functionality we expose. Well, the composition approach is much pickier about what functionality we expose. Additionally, if we don't want to expose 100% of the functionality, the composition approach basically forces us to choose, to say we want this, this, and this, but not the rest, whereas the inheritance says we want everything, and then you might have to override something and do a not implemented error or something like that. In the inheritance case, it can be a little bit difficult to remove capabilities. In the object construction approach, you can see this is the most general. We choose affirmatively whether we want F or G, and if we don't want G, we don't add it in here. If we want it, we add it in there, and we are explicitly responsible for sharing this, and it is our choice whether this is shared or not. Now, when you look at the object construction, you might say, this is a little bit phony baloney. I don't know that I would ever do this in real life, but in fact, this comes up quite a bit. When, for example, you are sharing this code via some sort of class decorator. What you've identified is every time you write a class, you do something commonly to that class. Well, that's a decorator. It's a class decorator. And the common thing you're doing is adding in extra methods. And the way you want to add in extra methods is not via composition or inheritance, but by object construction. Well, it's not too unusual to see a decorator which adds methods at class construction time using something not too dissimilar from what we called the object construction or the class construction approach before. Our conclusion is that anytime somebody tells you to prefer composition over inheritance, they're not telling you the right thing. Really, what you should think about when you think about these different mechanisms is, what are explicitly my needs? I'll give you an example. Let's say that I need to make a slight adjustment to how the pandas data frame works. Maybe I need to add just one method. Maybe there's something about the API that really irritates me. I can't remember if it's swap underscore levels or swap levels without an underscore, plural or singular. And you know what? I'm just going to make my life easier. I'm just going to write my own method called swap. And I want this to just shadow what already exists. So I'm just going to return super of whatever the actual one is, and I don't know off the top of my head, I think it's swap levels without the underscore, like that. Something like that. And what you could think is, you know what? My contribution here is quite minor. I'm taking all of that complexity of the data frame and adding one little piece here. Do I want it to be the case that an update to pandas adds another method to the data frame? When that update is added, somebody using my subclass complains to me and they say, oh, you didn't pass through that extra method? No, of course not. Here, using the inheritance approach is appropriate because what I really want to do is I really want to have any changes made to the base type automatically pushed onto me and then surgically override a couple of these. Inheritance is actually a very, very useful, if not necessary, approach in cases where you want to be largely transparent to changes that occur on the base type and only in some surgical places patch in some additional behavior, add in a little bit more stuff or modify some existing stuff. If you were to do this with a composition approach, which you've seen we do quite often in pandas, when you create some sort of data class or a named tuple that wraps around a data frame, well, the thing here is you would still be able to access these methods. You'd have to say A equals analysis, but you'd have to do that by doing a.df. And then the method that you wanted. And here you can say, well, you know what? For my particular use case, I don't really need you to know that there's a data frame back there. In fact, I'm not really anticipating that you're going to actually pass these methods through unless you really know what you're doing. Here, I want to be a lot more careful about what I expose to you. And this is why I might choose composition, because it requires that I affirmatively say, these are the pieces that I want to expose to somebody, and these are the pieces that I don't want to expose to somebody. That's largely the case why I might choose one or the other. There is another moderating influence here. A lot of the core types in Python weren't really written, at least in the third-party libraries like pandas and numpy and networkx and whatnot, weren't really written to be subclassed. Pandas mostly works when you subclass it, but it's not uncommon for some of the other types to not really work unless you subclass them and then override a bunch of stuff. I spoke about this in a presentation years ago called What You Got Is What You Got, and it shows you that the compositional use case can sometimes be a little bit tricky to use, as can the inheritance use case, because you can fall out of the derived type pretty easily. Now, in the case of pandas, this works pretty okay, and there's a couple of things that you might have to do if you were to inherit from pandas. Additionally, pandas provides you with some additional mechanisms like the registered data frame accessors, and you could think here what we're doing is we're patching into the underlying data frame type to add in extra functionality, and that might be our choice. It's not always inheritance or composition. There are often alternate approaches that we have, and our choice between these should really be dominated by how affirmative should I be? Is this a pull or a push mechanism? How responsible should I be if there are changes to my base type? Do I necessarily want to see those on my derived type or not? Do I need this to be interchangeable with, do I need this to be transparent with my base type, or is this its own thing with its own behaviors?